Welcome to Space Messenger. Today we are diving into the mesmerizing secrets behind the beautiful images of space. We've all seen those stunning visuals of the cosmos, vivid swirls and bright stars stretching across the black void. When you think about how quickly your smartphone captures a color photo, you might assume that complex space telescopes also automatically produce colored images. But this couldn't be further from the truth. From your smartphone to the James Webb Space Telescope, no digital camera can actually see in color. Digital cameras record images as a series of zeros and ones, counting the amount of light hitting their sensors. Each pixel has a colored filter that allows only certain wavelengths of light to pass through. These filters are arranged in a specific pattern, enabling the camera's processing hardware to combine the captured data into a full-color image. Some digital cameras spread the color filters across 3 separate sensors, combining the data into a full-color image. However, telescope cameras must capture images with a single filter at a time, requiring experts to combine them later. On our smartphones, this layering process happens incredibly quickly. But because telescopes are complex scientific instruments, achieving those familiar and beloved results takes a bit more effort. Moreover, when astronomers observe the universe, they often use wavelengths of light that our eyes can't even see. Therefore, these also need to be represented using the colors of the rainbow. There are many decisions to be made about how to colorize space images. This brings up the question: who makes these images, and how do they do it? When we talk about the stunning results we see from the James Webb Space Telescope, JWST, turning scientific data into beautiful color images is actually a full-time job. At the Space Telescope Science Institute in Baltimore, scientific visualization experts stack images and combine observations from different instruments on the telescope. They also remove artifacts, or things in the image that aren't real, caused by the telescope equipment and the way digital data is processed. These can include trails left by stray cosmic rays, the oversaturation of the brightest stars, or noise from the detector itself. Before even thinking about color, these experts need to balance the light and dark values in the images. Scientific cameras are designed to capture a wide range of brightness levels beyond what our eyes can perceive. This means that raw images from telescopes often appear very dark to our eyes, requiring brightness adjustments to see anything clearly. Once they have detailed black and white images, they start adding color. According to Katja Gozman, an astronomer at the University of Michigan, different telescopes have filters designed to be sensitive to specific wavelengths, and the colorful space images we see are combinations of separate exposures taken with these different filters, much like the camera on your phone. We can assign each filter to a color channel: red, green, or blue, the primary colors of visible light. When overlaid, we get those beautiful colorful images we're used to seeing in media and textbooks, Gozman adds. The research team often chooses different colors to highlight the various wavelengths observed by JWST's NIRCam and MIRI. For example, JWST's observations of the Cassiopeia A supernova remnant revealed a balloon-like feature emitting a specific wavelength of light, colored green in the MIRI image, leading to its nickname, the Green Monster. Without this visualization, astronomers might not have noticed such an intriguing feature that gives insights into how massive stars die. Overall, image experts try to keep everything as true to reality as possible. For visible light observations, wavelengths are directly matched to the colors we're familiar with. But for parts of the spectrum our eyes can't see, they have to make choices about which visible colors to use. This is where the work becomes a bit of an art, with colors chosen not only for scientific accuracy, but also for what looks best. The standard routine for JWST and Hubble is to use blue for the shortest wavelengths, red for the longest, and green for those in between. If there are more than 3 filters to choose from, sometimes additional colors like purple, cyan, and orange are added for the wavelengths between red, green, and blue. However, colorful images are much more than just pretty pictures. They are incredibly useful for science. Mark Poppenshock, an astronomer at the American Museum of Natural History, says the human brain is great at picking out patterns in color. Scientists want to use the same tool, but instead of social knowledge, this is scientific knowledge. If X-rays are red and ultraviolet is blue, we can quickly interpret energetic light beyond what people can normally process. The result is a visual representation of vast amounts of data, revealing much more than could be seen with the naked eye or in black and white. For example, Gosman describes how these images help recognize where different physical processes occur in a galaxy, like star formation or the distribution of various elements around a nebula. Color images of light beyond the visible spectrum have even revealed dark matter around galaxies, as seen in the Bullet Cluster. One particularly interesting case of image coloring involves Neptune. The dark blue photos of this icy world taken by the Voyager mission don't actually reflect its true color as if we were looking at it with our own eyes. It would appear more like the pale face of Uranus. Astronomers in the 80s adjusted Neptune's images to give more contrast to some faint features, resulting in that deep blue tone, which made it look very different from Uranus, Gosman explains. While astronomers are aware of this, the public was not. This shows how reprocessing the same data in different ways can lead to completely different representations. Image analysis has always been a significant part of astronomy, helping us see beyond the limits of human vision. NASA even makes JWST data available to the public and holds open astrophotography contests. So the next time you see a beautiful photo of space, you might think of it as a wonderful blend of science and art.